Presentation will focus on introducing various objects in the solar system, and then also I will give a flavor of as to how the solar system evolved to its present state, and how how did some objects, major objects in the amongst the inner planets and the satellites formed and evolved to its present state. And then and I will also tell about how one can date solar system objects. That is, determine the time scale of early solar system formed objects. So you can see this. You know, as you see the solar system, you start with the sun. This was described in some detail by Dr. Das yesterday, and then we have the inner planets, which are composed of Mercury, Venus, Earth, and Mars. And then comes the asteroid belt, and then you have the outer planets, which include the gas giants, Jupiter and Saturn, and then the ice giants, Uranus and Neptune. Now, Pluto is seen there, but Pluto now, as you know by now, is not considered a major planet. It's now a dwarf planet, as per the International Astronomical Union's definition. So solar system objects range in size from a few microns to which is basically regarded as dust, to giant planets. And information exists at all scales which tell us about the origin and evolution of the planets, which has been a basic research, a fundamental research area in the last 3 decades or so. In 2006, the IAU, the International Astronomical Union, has defined the planet as, it is given a proper definition that the planet must orbit the sun. Each planet must orbit the sun, and then it should be sufficiently massive, and it should have a spherical shape, and it should have cleared the region around its orbit of large debris. So now, because of the third property of this planet, of planets as classified by IAU, we now consider Pluto as a dwarf planet, and not as a planet, which was the case, 4 decades ago, or even 3 decades ago. So dwarf planets are the first 2 properties, but not the third criteria. So Pluto became a dwarf planet as is series. Now, then you have the asteroid belt, which is there between about 2.2 AU. One AU is basically 150 million kilometers. This is the distance. This is shown here. This is the distance between the Earth and the Sun, and most of the distances are classified. Most of the planets, when we talk about the orbit, we discuss in terms of AU, as you see here. So asteroid belt is basically between 2.2 and 3.2 AU. And these objects are very significant in the sense that they represent residue from the planet formation process, and they have undergone thermal or chemical processing. So I will come back to this table. Let's go to the formation of planets first. So at 4.5 billion years ago, to be very precise, it's 4.567, and we know this. This was a question asked yesterday, I believe. We know this because we can perform radiometric dating of early objects, early solar system formed objects. And there are also short-lived radionuclides, which can be used to date calcium, aluminium, CAIs, basically, inclusions. And then there are other objects which can be also used to date, like chondrules, which is one of the earliest formed objects. So 4.56 billion years ago, the solar system, there was a giant molecular cloud, okay, which contained interstellar gas and dust. The cloud collapsed, and then possibly due to a shock wave of a nearby exploding star, uh, um, which may have been a supernova, and then solar nebula forms, spinning, swirling disk of material. From this disk, then the sun forms, and then matter uh, 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 further out in the disk clumps form larger and larger objects. So some of them basically they will accrete. So you have planetesimals, which are very small objects which have accreted to form planets, and then you have other objects which are called dwarf planets and large moons which exist in the solar system. In some cases, the planets could not form, particularly in the asteroid belt, and there you have if you study asteroids, if you can go and have a sample return mission from an asteroid, then one can actually study one of the first solar system formed objects, and how it formed and how it originated and how it evolved to its present state. Other objects in the solar system are comets, meteorites, and moons. So if one looks at various characteristics of the solar system, so you can see there, okay, I have given certain colors. So you have the inner planets, which are labeled in rocky planets. These are basically rocky planets when you can see the densities there, okay. So if you see Mars has a density, this is the bulk density note. This is different from the crustal density, which for example, in the case of Moon is around 1.6, but the bulk density is larger because you have the crust, mantle, and the core. Right? So you have densities of the order of 4 to about 5, the bulk densities, and Moon is at 3.35. Then you have other objects, the gas giants and the ice giants, and note the densities, the difference in densities between the gas giants and ice giants. So now you also have the dwarf planets, okay, which are noted which are colored in orange or brownish, given, and these include Ceres, Psyche, Vesta, and Pluto. The mean radius of Ceres is 470 kilometers, and if you notice the gravities, basically Earth has, as you all know, Earth has a gravity at 9.8 meters per second square, and it has an atmosphere and a magnetic field, okay, associated with it. However, if you have a small object, then it is very difficult to hold the atmosphere, and therefore some of these objects are atmosphereless, as you will see in the forthcoming slides. The temperatures are given there, and this will be discussed in more detail later. Most of the planets have prograde motion, but there are the Venus, for example, is one which has a retrograde motion. So therefore, it is pretty slow. This means that basically, the central star, right? So you have the central star, basically, which is the sun, is moving, and all the other objects are moving in one direction, but the Venus moves in the opposite direction, clockwise, and the others are moving in the anti-clockwise direction. So therefore, it is slower, and there are reasons, and this is a big, there are debates as to how Venus, what gave rise to its retrograde motion, whether it is tidal locking between the sun and or basically tidal locking between Venus and sun, because Venus is very close to the sun, and the atmosphere heating, Venus is very hot and the atmosphere gets very hot. So therefore, these two forces are basically acting against each other, and therefore you have a motion which is opposite to that of the central star. Now, in this slide, I have outlined the mean radius, mass, bulk density, and orbit. And actually, this was a longer presentation last year, but I'm I have to note the time as well this time. So if you notice the surface temperatures, Venus, if you notice the sizes of Venus and Earth here, they are almost the same. The mean radius is of Venus is 6,000 kilometers roughly, and of that of the Earth is about 6,400 kilometers. So one may argue what led to this runaway greenhouse effect, which has affected Venus which has basically given rise to this surface temperature of 740 degrees. Why did Venus evolve to this state? And this is one of the major outstanding questions, which is yet to be resolved properly. So Venus surface temperature is 740, Earth is milder, and Mars is cooler because it is further away, 223 Kelvin. Mercury is the temperature varies between 100 to 700 Kelvin. At night time, you have very low temperatures, just as that on Earth, and not on Earth, on Earth's moon, and particularly in the permanently shadowed regions of the moon, where temperatures can be as low as tens of kelvins, about 40 Kelvin or 50 Kelvin or so. The magnetic fields, and you notice that Earth has a magnetic field it depends on where you are, so it's between 20 and 60 microtesla. The others, you see, the larger planets also have large magnetic fields, but Mercury doesn't have a magnetic field, and neither does Mars. Not a significant one. It's about 20 nanotesla, and on Mercury it's 300 nanotesla. And one of the questions is whether Moon had a significant magnetic field in the first 10 million years or so. So if we can do paleomagnetism of some rocks which are returned from the Moon, perhaps we can address this question. So if one looks at the atmosphere, the major constituents, you can see that Venus has a very thick atmosphere of 93 bar. But if you go about 50 kilometers above the surface of Venus, then the surface pressure is the pressure there is comparable to the surface pressure of that of the Earth. Okay, if you go to the Venetian clouds, Mercury has no atmosphere, the Moon has no atmosphere, and Mars has a 6.5 millibar atmosphere. This is at the surface. And the main constituents of Venus and Mars are carbon dioxide. Earth is the only habitable planet. So this is also one question. How did life originate, say about between 3.5 to 4 billion years ago? Why we have not detected any life on the other objects which we have explored thus far. And then you have Jupiter and Saturn, and maybe in one of these moons, okay, of Saturn, one may find a primitive form of life existing below the oceans. Okay, so I will move on more quickly. So asteroids and comets have origins from the solar nebula and provide samples suitable for dating formation of the solar system. Meteorites mostly originate from asteroid belt, but many are from the Moon and some from Mars, and some meteorites are derived from asteroids which have experienced differentiation. So you will hear about this in the next lecture from Professor Kuljit. And I'm just giving you some introduction. Chondrites contain spherical chondrules. So ferromagnesian, minerals, basically olivine and pyroxene, between 0.1 to 2 millimeters, and studies suggest that they solidify from a melt. And then you have a group of meteorites, HED, which is basically Howardites, Eucrites, and Diogenites, which originated from a single parent body, the Vesta asteroid, based on chemical classification. And then there are irons as well. which have come from the cores of asteroids, which have broken up as a result of planetary melting. So planetary bodies, as I've said, they form by accretion of grains that condensed from the solar nebula, and then centimeter-sized objects grew to meter-sized objects, and then kilometer-sized planetesimals, and then finally there were more and more collisions, and accretion led to the formation of larger-sized bodies of the order of 3,000 kilometers. So some fundamental questions I wish to put forth here as to why life originated on Earth. How did Venus acquire its dense atmosphere? Why Mars has a very thin atmosphere and Moon has no atmosphere? So maybe some of you can look into this. Let me go into now. I will discuss something about the origin of the solar system. So the first solids, if you look at even without dating, radiometric dating, if you look at the first solids to condense, these are refractory. Okay, so they have high melting points and low vapor pressure. So in nature, so the first solids to condense are shown there. Okay, corundum, perovskite. Okay, spinel. Then these are different minerals. Okay, and if one can date, if there is a way of dating the first form solids, okay, then one can tell the age of the solar system, which was a major question. Okay, so now, if you look at this, now I'm showing you different solids. Okay, so you have on the left, you can see refractory oxides, and then you can see pristine material, and then you can see that there are two things. One is differentiation, the other one is one body is differentiated, the other is undifferentiated. So differentiation is a process where basically you have melting of the entire or part of the object, solar system object, due to radioactivity and due to heat of accretion, if it's a large object. And then you basically can differentiate different kinds of objects. So because I have been limited to 35 minutes or so, I will skip some slides, but you can have undifferentiated objects. So this includes meteorite falls, which are chondrites and achondrites. And you can have differentiated objects, which include stony irons. So amongst these, okay, differentiated objects, you have Martian meteorites and lunar meteorites as well. And then the carbonaceous chondrites are extremely primitive, okay, ordinary and carbonaceous chondrites, and these are undifferentiated objects. So how do we actually analyze these samples? So you have, the samples are meteorites, okay, primitive meteorites, and sample returned from missions. And we will also have missions to the Moon, Mars in future, and other objects, solar system objects. And then one can analyze the stable isotopes, the radioactive isotopes, using the instruments which are mentioned here, and sample characterization can be done, which includes elemental and mineralogical composition. So just to highlight how this is done, okay. So basically, you see, there are isotopes. Okay, so aluminium-26 is the one. And, there's a lot of research which went on in the early 90s, and the next decade in PRL itself. Basically, aluminium-26 decays to magnesium-26 with a half-life of 0.72 million years. And based on this, you see, so if you have in this slide, you can see somebody asked regarding this. Okay, so this is this is how you can date these early solar system formed objects. So the first solids to condense were the refractory objects. Okay, and the time scale is linked to the origin of the solar system. So basically, if you want to detect these are relative time scales, okay? So what one needs to do is measure basically the aluminium 26/27 ratio in CAI. Here I've shown chondrule, of course. This is how you determine the time scale of age of chondrules. But basically, by looking at aluminium magnesium systematics, one can determine the age of these early solar system objects. So this will be discussed in more detail. However, let me give you a flavor before ending in the next 7 to 8 minutes. Let me give you a flavor as to how, what are the instruments which are flown and what are the objectives related to these instruments. Okay, so basically, what we do is we look at particles. Okay, that means they have mass. So we look at protons, alpha particles. We need to detect these, or we look at radiations, okay, and then waves. So these are the basic carriers of information which help us understand and detect subsurface features. For example, this is done using microwave, so radar, okay, synthetic aperture radar. Then you have the infrared part of the electromagnetic spectrum. So this is all related to the electromagnetic spectrum. Particles are, the particle domain is a little bit different. So one should differentiate between that and the electromagnetic waves, which are basically, these are composed of photons, which are massless. So you can tell about surface mineralogy by looking at IR, which is reflected back from the surface of moon. Okay, and you can tell whether there is water present, as was done and for the first time, in fact, water was detected by the moon mineralogy mapper on Chandrayaan-1. So this was the biggest discovery of Chandrayaan-1. And earlier there were some supporting experiments from neutron spectroscopy, but they could not conclusively tell because neutrons look at hydrogen. Epithermal neutrons tell us about hydrogen on the lunar surface. However, water is detection is only possible using IR or synthetic aperture radar, water or water ice, in fact, to be very precise. Then, if you go to X-rays and gamma rays, one can tell about near surface and subsurface chemistry. So, how did the moon? One can ask about how did the moon form? Okay, so basically, you have a Mars-sized impactor which hits the Earth and it blows out debris into the orbit. This is about 4.5 billion years ago, and it accretes, and then it accretes to form the moon. And this theory came about. There were many other theories. One suggested co-accretion. Then there was another theory which suggested that basically the moon was the moon was already formed. There were different theories anyway. I will not go into it now. But the lunar, the giant impact hypothesis satisfies the angular momentum of the Earth-Moon system. And it also basically came about because the oxygen isotope ratio was measured for return samples, and basically the Earth and Moon falls on the same line. So that provided conclusive proof as to this theory. And then why are the volatiles lost? This also can be addressed using this theory. Why is there the volatiles such as potassium? It is in much lower concentrations as that of the Earth. So then how does it evolve? Moon forms around 4.56 billion years ago. Then accretion melting results in the magma ocean. And most of the moon melted. And then crystallization of the magma ocean. So this is basically differentiation. And then you have cooling. And then you have basically a differentiated lunar interior. So you have the crust, mantle, and core. And the heavier minerals have sunk below, and then you have an anorthostic crust. But there are also features which have to be explained. And then you have impact cratering and volcanism. So there are several lectures which will address these, so I will not go into detail. This is the radiation which we expect. So you can see epithermal neutron, which is basically the energies of the order of 1 electron volt. So this can be used to tell the composition of the lunar surface and composition of surfaces of an atmospheric body. And this shows you the number of missions, okay, which orbiters, landers, rovers, and CubeSats which are planned as well. So you see there is a, in earlier, you had the Apollo and the Lunar missions, which brought back rocks. And from that, we understood how the moon formed. But then our ideas regarding the presence of water, ice on the moon changed when the M-Cube instrument detected water ice for the first time on our Indian mission, the ISRO mission Chandrayaan-1. And this has been followed by Chandrayaan-2 and Chandrayaan-3. And there are many discoveries which await us in future missions, which will take place, including that from ISRO. So some questions for you. Regarding lunar explorations, did the early flux of impacts. So we really don't know much about the time period between of evolution between 4 gigayears and about 2 gigayears. Okay, and we do not know whether the flux of impacts peaked at 4 billion years or not on the moon. So these are some of the major questions, and then we also wish to assess the mineral resources of the moon and volatile transport on moon. And two major objectives of sample return mission from a South Pole Aitken basin. It's a huge basin in the southern part of the moon. Is basically, if you date the South Pole Aitken basin, it places limits on the early impact history and timing and duration of basin formation events. And then this is the deepest basin in the solar system. So you may have 12 kilometers or so, and you may expose the lower crust and the upper mantle. So you will get to know, you will get a better understanding of the upper mantle if you study rocks brought back from the South Pole Aitken basin. As regards Mars, I will not tell much, but what we do not know, and this is the second last slide, so I will conclude soon, is how, when, and why the environments vary through Martian history. And did any of them host life or its precursors? See, Mars, initially, it was hot and humid. It had a much thicker atmosphere than the 6 millibar atmosphere, which is prevalent today. And basically, solar wind erodes the atmosphere, because the Earth has a magnetic field, but other objects such as Mars or the Moon, they don't have strong magnetic fields. So they are not protected from particles, okay? Such as solar wind protons, which come into the atmosphere and then erode the atmosphere significantly through time. So how has the Martian climate evolved through time? What are the inventory of carbon compounds? Is there life on Mars? Did life exist on Mars? That also, but now that is moving towards then there were questions regarding follow the water, and then which parts of Mars are habitable? So these are some of the questions. Then what is the internal structure and dynamics, and what are the nature ages and origin of diverse geological units? And here you can see there are less Mars missions, and we have our Mars orbiter mission as well, MOM, which was flown in 2013. This is likely to be followed by a lander rover mission in the near future. And we will have many more discoveries, and I hope some of you will be motivated to contribute to the planetary science and the solar science exploration, solar system exploration program of ISRO. Thank you.